My dear students, we are going to study Tafel's theory of hydrogen overvoltage. The cathodic evolution of hydrogen was first studied by Tafel in 1905. It is observed that for evolution of S2 at cathode from the aqueous solution of electrolyte, some extra potential has to be applied than predicted theoretically. This difference between actual potential required for evolution of S2 at a particular cathode and expected reversible potential is known as overvoltage, also known as overvoltage for bubbling of S2 gas. The potential in excess of the reversible potential is required to discharge hydrogen ions at the cathodic surface, known as hydrogen overvoltage. It depends on the chemical nature of a cathode and the current density. The plot of surface known as hydrogen overvoltage. It depends on the chemical nature of a cathode and the current density. The plot of overvoltage eta against current density I milliampere per centimeter square indicates that the overvoltage increases with the increase in current density. When platinized platinum is used as electrode and if the current density is 0, then the hydrogen overvoltage will be 0. This is because of the reversible nature of hydrogen electrode. As current density increases, the overvoltage only marginally increases for platinized platinum, but for a smooth platinized shows a rapid increase. Same is the case with gold, graphite and palladium electrodes. However, for various metals like silver, bismuth, tin, iron, mercury, cadmium, zinc and lead, the overvoltage is very high even at 0 current densities. The hydrogen overvoltage has a great importance in the electrogravimetric determination of metals such as cadmium and zinc. The mechanism for the continuous discharge of hydrogen ions at the cathodic surface may be given by the following steps. The transfer of H plus ions from the bulk of the solution towards the electrode surface at the vicinity of the electrode. The discharge of these ions at the electrode surface, transfer of electrons from the electrode to the H plus ions present at the surface producing H atoms, discharge of the ions to form atoms, adsorption of H atoms at the electrode surface, conversion of H atoms at the electrode into S2 molecules, evolution of S2 molecules from electrode in the form of bubbles. The discharge of hydrogen ions at the cathodic surface depends on the nature of electrolyte solution. This can be explained as follows. In an acid solution, the hydrogen ions are hydrated H3O plus, that is associated with the water molecules. Therefore, the reduction reaction is represented as H3O plus, means a hydronium ion plus electron gives a half H2 gas plus H2O. Or net electrode reaction is H plus plus electron, it gives half H2 gas. In alkali solution, the reaction is different, that is H2O molecule undergoes a reduction to liberate hydrogen gas. The reaction is represented as H2O plus electron gives a half H2 gas plus hydroxyl ion, that is OH minus ion. If all the above reaction occurs rapidly, then and only then the potential will tally with the expected reversible potential. However, conversion of H atoms to S2 molecule at the electrode is a slow process, that it is a rate determining steps, since H atoms do not get converted to S2 molecules, which is a catalytic process. It is necessary to activate cathode by applying extra potential. At the same time, due to the accumulation of H atoms at the electrode, the resistance of the system increases and hence extra potential is required to continue the electrode process. Based on the theory, Tafel suggested a relation for S2 overvoltage and current density known as Tafel's equation. This expression applicable for variety of electrodes. Eta is equal to A plus B log I. Eta is a voltage, I is a current density, small a and small b are the constants for given electrode under given conditions. The eta is equal to A plus B log I. The value of A varies from 0.1 for platinum to 1.5 volt for lead. The value of B is constant for most of the metals and is equal to 0.12 volt. B is equal to 2.303 RT divided by alpha F is equal to 0.1184 is equal to 0.12 volt at 298 Kelvin. B is equal to the slope where alpha can have values between 0.2 and 3. The equation is of type is equal to y is equal to mx plus c is equal to y is equal to c plus mx. The plotting the graph eta is of type is equal to y is equal to mx plus c is equal to y is equal to c plus mx. The plotting the graph eta versus log I, then the validity of equation can be tested by plotting a graph of eta versus log I. As the plot of eta against log I gives a linear plot, a straight line making intercept on y-axis. Intercept of y-axis is equal to small a and the slope of a plot is equal to b, small b. Then a variation of overvoltage eta versus log I plotted. The term A of small a of the Tafel equation is found to be totally dependent on the cathode used. Apart from temperature, current density and the cathode used, the overvoltage is found to depend also on the nature of the surface of the cathode. Hydrogen overvoltage in a normal HCl solution at current density 1 milliampere per centimeter square. Electrode, then hydrogen overvoltage in a volt. For example, electrode platinized platinum 0.01 volt, smooth platinum 0.25 volt, nickel 0.33 volt, iron 0.40 volt, copper 0.54 volt, lead 0.88 volt, cadmium 0.99 volt, mercury 1.04 volt. Factors affecting the overvoltage. First, that is the current density. The overvoltage increases with increase in current density. Eta is proportional to the I. If hydrogen is not removed by reaction with oxygen or any oxidizing agent, then overvoltage increases with the increase in current density. pH of the solution. In a strongly acidic or alkaline solution, deviations occur due to a large concentration of H plus ion or OH minus ion near the electrode. The third factor, that is the temperature. Since overvoltage is due to a slow process, slow stage of discharge of H plus ion, that is eta decreases with increase in temperature. The change is approximately 2 millivolt per degree. The next factor, impurity. Overvoltage is susceptible to the presence of impurities in the cathodic materials. Next, that is the pressure. It has been observed that at a higher pressure, overvoltage is slightly affected. However, at low pressure, it increases rapidly on cathodes of copper, nickel, etc. Then next, that is the surface. As the effective surface area of the electrode increases, the overvoltage decreases. On smooth, even and polished surface, the overvoltage is greater than on a rough, uneven surface. For example, the hydrogen overvoltage with platinized platinum with dilute sulfuric acid is 0.05 volt, while on smooth platinum with the same solution is 0.09 volt. Thank you.